Hello everyone, welcome to a new episode of our ISO tutorial series. And I'm really looking forward to today's episode because we're going to do pathfinding and we're going to use my favorite algorithm, Dijkstra's. So we'll see an implementation of that algorithm and how we can start using it for pathfinding going forward. So let's get started. So, for those who don't know Dijkstra's algorithm, it's an algorithm that can help you find the shortest path between 2 points. And although there are really good explanations of the algorithm on the internet, I'll do a very quick rundown. The idea is that if you have a map or a graph, as Dijkstra called it, you can determine the distance between each and every node based on where you can go. So to start, if you have a flat map like this one, a Dijkstra map would be constructed something like, let's say we start at the top left. We give this one a distance of 0, and on one next to it will have a distance of 1 because we can go there in one step. And also going down also has a 1. But if you want to go to this one, for instance, you have to first go to this one and then to this one or through the other one. So this becomes a 2, providing we assume that you can only go east, south, west, and north, not in the diagonal directions. And basically you can fill up the map like this, and this map is really a trivial example, but it's a good start. Sorry, 2, 3, 4. So this is a Dijkstra map for completely flat map. That isn't very interesting yet because this is not a terrain that has any obstacles in it or any height difference that might matter, but we'll get to that in a bit. I also created one for reference here, just to see if I didn't make any mistakes setting this one up. So let's start by creating a test that will validate that we can transform a flat map into a Dijkstra map. So let's go into our map tests and we will create a new section called pathfinding. And let's create the first test. So we'll create a Dijkstra map that when we don't have any height differences. So to summarize, this is our height map and this will be our Dijkstra map. And how to transform from a Dijkstra map to a path is something we will explore in the next episode. For now, this is about distances only. So let's create a new map. And this map will be a flat map. And we will get back an expected Dijkstra map. From a starting position, in this case, we will start at 0, 0, that's the top left position. And we will have an expected result. This will be also an array. And we can use our reference. Now we can go through each coordinate. and we can assert that our Dijkstra, which doesn't have a value yet because it doesn't have any, this function doesn't exist yet. But this will be a map that takes a coordinate and compares it to the expected result at the same coordinate. So let's create a stub for the Dijkstra function. And this will take a target. And this will return a map of vector 2Ds to an int, where the integer is the distance to reach a specific location. For now, let's return an empty dictionary so we can at least have something that compiles. We need to assert these are equal. Right. And let's quickly run the test. Okay, of course, the test fails because we're not returning. We're returning an empty dictionary, and those will never be the same as the values here. No problem. Let's implement Dijkstra properly. The algorithm starts with setting up a few sets. We have an unvisited set. These will be coordinates that we still need to check, and we have a visited set. This is also a set of vector 2Ds, and we have a distance dictionary that maps from a coordinate to a distance, and it's that one that we return at the end. So this is similar, more or less, than what we had. We're still just returning an empty array. So let's make sure we populate the distance dictionary as we go along. So we start by inserting our target as the first unvisited coordinate. Also, we define the distance to the target as 0. That is a start case. Then we create a variable holding a current node. That's the current location we're working from. And then we can start the actual algorithm. The idea is we continue until unvisited is empty. So as long as it's not empty, there's still stuff we need to check. And we need to check because it's currently holding the target. So the first thing we do is we get the neighbors of the target. So we should have a function returning neighbors for the current node. Let's implement it. Function. This takes in a node and returns an array of coordinates. And ideally, we take our vector 2D and we make sure that we can get neighbors of a coordinate, and this returns an array of four Cartesian neighbors. So we now get 4 coordinates. going east, going west, going north, and going south. We can use this one in our map get neighbors for function. So we'll take node neighbors, but we will filter out the ones that are outside of the maps and location. And we can do that by saying tiles.keys contains neighbor. So it should be one that's defined in our map. That way we don't go out of bounds. So now we have a set of neighbors. The next step is to go for each neighbor, and then we check if it's one that we already visited. We don't do anything, but if it's one that we haven't finished yet, so visited contains neighbor equals false, then we insert it in the unvisited set. So now we have something more to check. Also, we check what would be the possible distance to this one. We take the current node's distance value, and we know that this one, we can force unwrap this one because we make sure that this one is also set. And then we need to determine the additional cost to go there. For now, because this is a flat map, the cost to go to the next one is always 1. So we take the one we already have and then add 1. And then we check if this is a better way than having our current neighbor's distance. And if we don't have it yet in our system, we can always take the maximum integer value. That way we will always set it, and we can say the dist for the neighbor is equal to this alternative. Then we go to our unvisited set and remove the current node, because this one we now checked, and we take the visited one and we insert the current node, so we keep track of which one we checked. And then we need to check create a new current node, or see what's the next current node will. What we'll do is we'll find a new node. We take the unvisited nodes, and we take the one with the lowest distance. And we do that by finding the minimum distance for the node with the default value maximum, meaning that if we have one defined, it will always take that one, and we compare that to the to another one. And if this finds us a new node, our current node will be the new node. And finally return the distance. So a lot of code. This is the basic algorithm. So we should now have a correct map. So the test passes. Let's take it up a notch, and let's look at a height map that has height differences in it. So we have here a map with an elevation, and it starts more or less the same, because the first row is still just all the same height. The second row will be a bit different. So going from to this one is height difference of 2, meaning that we need to add 1, and going to this one also, and to this one we can. The last one is a bit interesting, because we could go there from this coordinate, meaning there's a height difference of 1, meaning that this would then be, for instance, a 6. However, we can also go through this one, and that has a lower cost, and that's why we choose the 4 here. We do something similar here. We have a difference of 2 here, So we do 6, and the last one is cheapest to go through the top. And this is where you sort of start seeing paths emerge. Finally, this one is really obvious. Now let's quickly check our reference version. Looks like that's the same. So let's write a test that takes the height differences into account. So we can just copy all this stuff. But this time we do width height differences. So we need a different map. And we have a different, oh, that's the Dijkstra map, not, and I need this one. This is the height map. We have our references, reference version here. And if we test this, this will not work because the costs calculated are not correct. So in certain places we get the wrong values. What we need is a cost function, and the cost function is basically what it takes to go from one node to another. And we can create a function for that. We create a cost function that goes from one vector to another vector and then returns an integer. And our function will be 1, at least 1, plus the difference between in elevation between from and to. And taking the absolute makes it that we always get a positive value that shows the distance between those differences in elevation and not getting negative values. So we always get 1 at least. So for a flat map, the cost will still always be 1. But for instance, in this map, if there's a difference of 1, we add 1 and then we get the 2 as a cost. So let's use this one instead of doing plus. We can do the cost from the current node to our neighbor. And this test should now work. Now, for now, we only used the upper left as the target location. This also works if you choose a different location. So let's say we start at this position. Then this one would become 0. I think that would be this one, and we could build up the map from there. So I'll just go to the reference because that's a bit easier. So let's copy this test, and with height differences, and we're starting elsewhere. So we use the same height map, but we do a different target location. And we'll go to 1, 2, and we have a different expected result. This needs a label. So we have a different expected result, and this test should also pass. Okay. Now this also works for the example height map we have. So let's quickly validate that. So we have our example map. And what we can do is we can copy all this stuff, but the map will be based on our self.example height map. That means we have a different expected result. This one. And this one should also work. Until it doesn't. Oh, I think because this one too, the reference is looking from 0, 0. Okay. Fortunately, that works. Now, Dijkstra has the assumption that it's a slow algorithm because the complexity increases a lot depending on the size of your map. So talking about pathfinding in games, typically algorithms like A-star are used that are sort of optimized versions of the Dijkstra's algorithm that help do pathfinding in a slightly quicker way. The reason why we're not using it here is because although A-star is really good at finding a path from one position to another, the Dijkstra map has additional features. One in particular is finding very quickly all the places where you can go. Because, for instance, let's say I have a unit that covers max distance of 4. Let's say it's on this position, it's very easy to find all the places where it can go, because that's simply every value 4 or less. So all the ones that are higher are basically blocked out. And this is the map of all the places that you can go from starting at 0, 0 with a max distance of 4. So by using this instead of A-star, not only can we do pathfinding, but we can also very quickly determine where you can go from a certain position. And that is useful if you want to show to the player all the potential positions a unit can move to. Okay, talking about performance, let's show quickly something about the performance, because it's not as bad as you might think. So let's say we have a height map that is 100 by 100. Let's create a map from this height map. And then we can use the measure function from XCTest. Test. So keep track which run we're at. And we'll take a target that can be anything. Let's take a random one. And then increase 1. And let's run this test for a bit, just to give you an idea. These take about 0.2 seconds to create for a 100 by 100 map. That is actually really, really large for a game like this. In Pocket Tactics, the maximum map size I use is 32 by 32. That's already pretty big. Doing it with a value like that is like almost instantaneous. So for now, I'd say don't worry about performance, and it gets even faster if you have impassable terrain, because those ones don't even get evaluated. This is like the worst case scenario where every tile is reachable. So we have our pathfinding. Let's see if we can also show it a bit in our game. So at least let's make sure that we can show the actual Dijkstra map. I'll close this one and then add some temporary stuff just so we can show the Dijkstra map. So we'll take a Dijkstra variable, that's a vector 2D and an integer. And we'll keep track of a selected coordinate. This is an optional vector 2D. And now let's go into our redraw function. And create a Dijkstra map if the tile is selected, just to show it. So if let's selected the coordinate, then we create a Dijkstra map. Else we will clear out the map. And for now, let's just say our selected coordinate is 0. Just so we can see it. Then we need to make sure that we can show it on the screen. So let's add some stuff here just to show the Dijkstra map. So this is all stuff that needs to go later. We need to create a color. We default it to white. If there's a distance in the Dijkstra map for our position, then we create a U, and this will be the distance as a double. I experimented with various numbers, but using 10 gives a nice big change in colors to make it really visible. Then we can set the color to U, saturation of 1, brightness 1, alpha 1. Then we need to set the sprite blend, color blend factor to 1 and sprite color to color. And we can run this. And now we should see a Dijkstra map from coordinates 1, 1. I'm sorry, coordinate 0, 0. So that's this one. If you rotate the view, that one sticks. And you can see basically the values moving up as you go further away. And it isn't completely a linear rainbow because costs to go into the higher ones are different. So far so good. I think it would be cool if you could click on a tile and then recreate the map. So let's go downstairs and quickly make a first pass as at our touches began function. This detects touches to the screen. So first we see if we can find the touch, and if not, then we return. Then we need to convert the touch to a point in the scene. There's a function for that, convert from view, and the view will be our touch location in our own view. Then we try and find a node. Otherwise we return as well. And we try and find a coordinate. And the easiest way to do is to simply make sure that the coordinate is stored in a node. So we try and get the coordinate out of the node, and if it doesn't work, then we return. User data is an optional, so it needs to be unwrapped. Then we have our selected coordinate. We can set it to coordinate the XY because this is a 3D coordinate and we need a 2D one. And then call redraw. Now, this doesn't work yet because we're never setting this user data, but we can do that up here. We can say sprite of user data is coordinate to position. This associates the tile with its coordinate. And this way we can click on stuff and select the tile. Now this touches begin implementation doesn't work correctly yet because it doesn't take into account overlapping tiles very well, but that's an issue for later. So we can click on a tile. Let's see, we should be able to click on a tile. What am I missing? Let's debug for a while, for a bit. So let's click. Okay, so we have a touch. We have a scene point. We should have a node at that point. We should have a coordinate. We have a selected coordinate. Oh, I know. This is working. However, we are still hard coding or overriding it there. Okay, so we can click on one and the map changes based on where you click. As you see, the clicking isn't working very well. The reason for that is that this way of determining where you click gets confused by overlapping tiles and overlapping nodes such as the units. But the basic idea is there that depending on where you click, you get a different map showing the distance from where you click to somewhere else. And we will definitely improve this function to be a lot more robust. But this is enough for now because now we have the Dijkstra Maps and we can use that to construct paths in the next episode. So thanks for watching and have a good day.